Okay, we start with review of the concepts. So those who are very good in concepts, you can look at this, you can wind up the session. Those who want to learn more about it, you can go deep into the video. So you see, what shall be covered in this particular video is that we shall see how atomic orbitals combine, the reason behind atomic orbitals, or I shall give you a good understanding on how to understand the atomic orbitals combination using linear combination of atomic orbitals is LCAO method. So you see, n atomic orbitals and n atomic orbitals can combine to give you 2 n molecular orbitals. So molecular orbitals are for molecules, atomic orbitals are for atoms. So out of them, half is for bonding and half are for anti-bonding. Now how do you account for, what do you call, or what do you mean by bonding or anti-bonding molecular orbitals? By the overlap conditions. See, if two molecules are going to overlap constructively, it leads to bonding molecular orbital, which is a stabilizing orbital. Destructively, if they overlap, it leads to an antibonding molecular orbital, which decreases the stability of the my system. Now, orbital overlap conditions. We saw how s orbitals or how s and p orbitals, s and p or p and p, p and d or s and d can all overlap. What types of bond can be formed? What is meant by antibonding and bonding? Sigma, sigma star, pi star, those things. Then bond order. Bond order, this is very important. Bond order is directly proportional to bond strength. Greater the bond order. When I say bond order 3, bond strength is high. When I say bond order 1, bond strength is low. Then bond order is directly proportional to bond stability. So greater bond strength means it's more stable. Yeah. Then last one, energy. Bond order more, lesser energy. So when you say a molecule is very stable, that is having lesser energy. So they are inversely proportional. Bond order, energy, inversely proportional. Bond strength, energy, inversely proportional. Bond stability, energy, inversely proportional. Then we saw what is meant by paramagnetic and diamagnetic, and how to say a molecule from paramagnetic and diamagnetic by looking at the molecular electronic configurations. So when you see even one electron unpaired, you call it paramagnetic. You call the entire molecule paramagnetic, and you have a magnetic moment value for it, right? Then when you see paired electrons, you say it is diamagnetic. Now bond order for polyatomic molecules. How do you find the bond order? By using a simple formula. Polyatomic molecules are molecules with more than 2 atoms. So for them, there is a simple formula. Just by you have to draw the structure first. Correct structure should be drawn according using BS-CPR theory. Now, how do you find the bond order? Total number of bonds attached to the central atom, or you just count, just see, locate the central atom, see how many bonds are attached, divide them by the number of atoms attached. Okay, so this is a very short review of what shall be covered in this particular video. Okay, so happy learning. Now we are going to learn how to put electrons into our molecular orbitals, and how to predict the magnetic nature, how to predict the electronic configuration, and how to predict the bond stability and energy of our molecules. Okay, let us proceed from a very simple example, a hydrogen molecule, H2. So you know, hydrogen molecule is a diatomic molecule, and it is composed of 2 hydrogen atoms singly bonded. This is the information that we know already. Let us test this, or let us learn more about this hydrogen molecule using our molecular orbitals. So before that, you should know the electronic configuration of our hydrogen atom. You know, it is 1s1. So here I have got a small set of lines representing my atomic orbitals and molecular orbitals. The yellow ones are the atomic orbitals, and the middle ones, the white and the red one, are the molecular orbitals. So first, let me fill the atomic orbitals. Atomic orbitals have to be filled from the atoms. So here, atomic orbital of one hydrogen atom, atomic orbital of another hydrogen atom. What is the configuration? So what is my orbital? It is 1s orbital. So I take 1s and 1s. How many electrons do I have? 1 electron. So fill in the electrons as well now in the energy levels. Now, this having done, I have to just plain addition of the electrons and put them into the molecular orbitals. So, how do I do that? 1 plus 1. Now, before putting them into the molecular orbitals, remember the Pauli exclusion rule, remember the Hund's rule, and remember the Aufbau building principle. So, you have to always build the electrons from the lowermost to the higher energy levels, and you also need to ensure the pairing. That is, once the lower energy levels are paired, then go for the higher energy levels. Otherwise, we have degenerate levels like orbitals of same energy level, put single electrons on each, singly paired electrons on each, then you have to pair them. So all these rules need to be followed. And one more thing, this is one orbital. One line stands for one orbital. One orbital can hold a maximum of 2 electrons only. So follow these rules and come on, let's do it. So 1 and 1, I'm going to fill it here. So when 2 atomic orbitals join, you get 2 molecular orbitals. When 3 join, you get 3. So the number of, it's like addition, just like addition. The number of combining atomic orbitals will always be number of obtained molecular orbitals. Okay. So 2 molecular orbitals for 2 atomic orbitals. These are 2 waves of atomic orbitals. These 2 waves are going to interfere constructively and destructively. Constructively to give the bonding molecular orbital and destructively to give the anti-bonding molecular orbital. Now I have to name the atomic orbital. No, they cannot be, because I can have for 1s this is one molecular orbital set. For 2s I might have another. For 2p I might have another. So I have to distinguish it. So I am going to name it using this kind of a notation. See, for bonding molecular orbital, I name it saying it is sigma 1s, because the sigma bond is formed from 1s orbitals. And for the anti-bonding, I name it the sigma star 1s. Why do I say sigma? Because it is 2 s orbitals overlapping and they are going to overlap effectively. So they need to head-on overlap, and that is a sigma bond. And sigma star is just to say that this bonding is anti-bonding. And I have given red color to imply that any electron you put into the anti-bonding molecular orbital is going to be bad for your system. Okay, it is going to be destabilizing for your system. So put your electrons into the bonding molecular orbitals. The more electrons in the bonding molecular orbital, more your molecule will be stable. So to talk about the stability, we have a term called bond order. What is bond order? Bond order tells you the strength of the bond. See, here, hydrogen forms one bond. That is, 2 hydrogen atoms form a single bond between each other. So you call the bond order of hydrogen to be 1. How do I find bond order for other molecules without knowing much about them? Always bonding minus anti-bonding, because you're going to fill from the bonding level. So this is going to have lot of electrons compared to anti-bonding. So bonding minus anti-bonding will give you a value. Take half of that. That is going to be a bond order. So here our bond order is half into 2 minus 0. So it is 1. So a bond order of 1 can tell you that there is single bond. A bond order of half can tell you that there is a partial bond, not a complete bond. This is bond order of half. A bond order of 2 can tell you that there is a double bond. And these are all not true. So bond order can be obtained from this kind of molecular orbital theory that helps us give the electronic configuration of a molecule. See, electronic configuration of atom is 1s1. Now we shall write the electronic configuration of the molecule hydrogen. So what is it? H2. The electronic configuration is using the molecular orbitals you need to write. See, the molecular orbital is sigma 1s for the bonding. So again, writing, go from the lowest energy. So it is sigma 1s. How many electrons in sigma 1s? 2. So sigma 1s 2. Then next level, molecular orbital, I have sigma 1s star. Then you write sigma 1s star. How many electrons in that? 0. So 0. So this is my molecular configuration. Okay. Next we shall learn about the property, molecular magnetic property. When we talk about the property of this molecule, there can be 2 things, diamagnetic or paramagnetic. For that, you need to look at the molecular orbitals only. Remember, for diamagnetic or paramagnetic properties, look at the molecular orbitals. See, in the molecular orbitals, my bonding molecular orbitals has 2. It is paired. It has got it has got a pair of electrons. They are paired. So here, I will say my molecule, hydrogen molecule is diamagnetic. paramagnetic species can be repelled by the magnet. So when you keep this hydrogen molecule or when you liquefy hydrogen molecule and you flow it through magnets on the sides, they are going to be repelled by the magnet. Okay, so they are diamagnetic. That is because the electrons are paired in the molecular orbital. Suppose you find the electrons are unpaired, that is single. If you find single electrons in the molecular orbitals, you call them paramagnetic. So this is with respect to hydrogen. Now we shall see little bigger molecules. We shall now learn about the molecular orbital diagram construction for O2 molecule, one of the most important molecules. So for O2, first we write how O2 is formed from two oxygen atoms. We do not know what kind of a bond is formed, but we know in O2 there are two oxygen atoms. So what is the configuration of oxygen atom? 1s2, 2s2, 2p4. Now we are going to have a set of atomic orbitals like, see, 1s2 of one oxygen is going to overlap with 1s2 of another oxygen. Then the 2s of one oxygen with 2s of another oxygen. 2p with the other 2p. So this is how we are going to merge our atomic orbitals to get the molecular orbitals. So first, like we saw in the hydrogen case, I have taken 1s and 1s. So you know 1s2, no? So I am going to draw two electrons here. Now you see there are 4 electrons in 1s. So the 4 electrons have to be distributed in the molecular orbital, like 2 over here, the other 2 over here. So now you see what happens when I fill this way. My 1s molecular orbitals, the bonding as well as antibonding, both are filled. So you know, I told you already, filling the red line, filling the antibonding level is dangerous. It's bad for the molecule. So this filling here would mean that the bonding effect is cancelled by the antibonding effect. It is equal. Constructive interference is equal to destructive interference. So they cancel each other. So it is like nothing has happened. So here you see the configuration for the system is, this is sigma 1s, this is sigma star 1s. So how to write the configuration for this particular small system? Sigma 1s 2, sigma star 1s 2. So this sigma and sigma star, this particular configuration is the basic, you know. For every molecule, this configuration is going to be there. So I take this as equivalent to Kk. This Kk denoting the K shell. No, this is the K shell. First shell, 1s, that is the first shell, first period. You call it the K shell. So the simplest form of writing this configuration is Kk. Now come to the second. We are going to take atomic orbitals, 2s atomic orbitals, and see 2s again the same way as we did, 2s2, here also it is 2s2. Now putting the electrons in it. So here first 2 electrons, then the other 2, totally 4 electrons are put. Again here you see the bonding is cancelled by antibonding. 2 bonding, 2 antibonding cancels each other. So the configuration I will write. Here for this, how do I name the molecular orbital? The lower molecular orbital is named as sigma 2s. This higher antibonding is named as sigma star 2s. Okay. So the configuration is sigma 2s to sigma star 2s. Now coming to 2p. What is the configuration of 2p? Every 2p has 4 electrons, 2p4. So first I fill it. See here you can see three orbitals are there. So how do I fill the 3 orbitals? See 1, 2, 3. Then fourth one here. 4 are filled. Similarly on the other side. So it is all these are degenerate. Remember the p orbitals are degenerate. They are equal in energy. So 1, 2, 3. Then you have to pair. First simply put the electrons in a degenerate orbital, then you have to pair it. Now count total electrons. Here 4 and here 4. So 4 plus 4 is 8. All the 8 must be accommodated in the molecular orbital. Let us start doing that first in the lower level. See, now when I have 2p merging, you know what is that I have? In 2p, you know, there are 3 orbitals. Or in p orbital, there are 3 subshells, right? One is called the px, the py, and the pz. See, when anytime, you know, the px and py and pz are perpendicular to each other. So, when one orbital can form sigma bond, the other 2 orbitals cannot form a sigma bond. They have to go by a pi bond. So, that is with respect to alignment of the orbitals. So, here any one of the bond only is any one of the bond only can form a sigma bond. The other 2 will form a pi bond because of their presence. Okay. So PZ is going to form a sigma bond here. Usually PZ forms a sigma bond. So here, the lower bond here is the sigma bond formed because of PZ. So I call this as sigma 2PZ. Then the other two bonds formed by PX and PY, they are going to be pi bond. So the pi bond formed between both of them there are two bonds, PX with another PX, PY with another PY. This is going to be pi bond, and PZ with another PZ is going to be sigma bond. So I have two pi bonds. You remember both the pi bonds. So this is a pi bond, this is a sigma bond. So they can have different energies, but both are pi bonds. They are going to have same degenerate energies. So that is why I have two bonds, two lines in the same energy. So both are, I call them pi 2px, pi 2py. So this is sigma, this is pi. Always remember, sigma is 1, pi can be degenerate. So the above ones can be antibonding. This is again pi star, this is sigma star. So now I start to filling the electrons. It is 8 electrons, I start to filling them. So I get 1, 2, then 3, 4, 5, 6, 7 and 8. So 8 electrons are filled. Okay, here you see 8 electrons are filled. And how they are filled? The antibonding has 2 electrons. The bonding, all the 6 electrons are filled in bonding. 2 electrons only are the antibonding. Now, how do I find the bond order for the whole of my oxygen molecule? So, very simple. What usually we used to do is count all the bonding electrons, count all the antibonding electrons, subtract them and divide them by 2. But you don't have to do that. See, oneness you see bond, I told you bonding cancels antibonding. Both of them cancel each other. So I don't have to count this. Come to 2s. Again, bonding, antibonding are equal. So you cancel it. If bonding and antibonding are going to be equivalent, they don't contribute for the bond order. So coming to this. Here you see how many bonding are there? 6. Antibonding 2. So this alone can be done. So how do we find the bond order? It is half into 6 minus 2. It is 2. So bond order is 2. That is why we say oxygen forms O double bond O. It is divalent. Oxygen forms a double bond with another oxygen. And this bond is quite strong because being a double bond. Now let us talk about the magnetic property. Look at the molecular orbitals. Here you see there are 2 electrons singly standing. No? So these 2 electrons account for the paramagnetic nature of oxygen. Paramagnetic. Because of paramagnetic nature, oxygen is attracted by a magnetic field. Okay, paramagnetism, it is attracted by the magnetic field. Now how do we write the configuration? Like, how do we write? Instead of the first oneness, for the oneness molecular orbitals, Kk is sufficient. So I write it here. For the O2 molecule, the configuration is Kk, then sigma 2s2, sigma star 2s2, then sigma 2pz2, then pi 2px equal to pi 2py 4, right? Pi 2px and pi 2py both are equal in energy, so I can have them put them this way. They are equal, and the total electrons they bear is 4, and then the antibonding levels, pi star 2px equal to pi star 2py, and they amount for 2 electrons. This is the configuration, and this is how I solve the problem for my oxygen atom. So oxygen molecule. So coming to this, oxygen is very, very important. So you have to remember that for oxygen, all the bonding levels are filled. Only 2 electrons are put in the antibonding levels. Now the same question can be asked, like find the bond order for O2 minus. Now when you see O2 minus, there is minus, a negative sign indicates 1 extra electron. So what I do, you remember this particular configuration has to be remembered. That is, bonding electrons are all filled, antibonding there are 2. Now The minus charge denotes one extra electron. So from in the same O2 MOT, I am going to put one electron extra. So now what happens when the calculation changes, correct? For O2 minus, it is half into 6 minus 3, which is, so for O2, the bond order is half into 6 minus 3, which is 1.5. Or for any of the oxygen molecular ions, what I can predict is, the more I add electrons to the antibonding level, the bond order will reduce. You see, first for O2, the bond order was 2. For O2, the bond order is 2. For O2 minus, one extra electron, the bond order reduces. For O2, 2 minus still reduces, becomes 1. So the more electrons you add to the antibonding level, bond order will decrease. Then when you start removing electrons from the antibonding level, suppose I remove the electrons from the antibonding level, my bond order will increase. That means the bond will become more stable, more stronger, and less in energy. Okay, so this is about the bond order and other aspects for the oxygen molecule. And remember, for oxygen the pattern is sigma down, pi, then pi and sigma star, pi star and sigma star. For other, now we are going to see for other molecules like nitrogen and below them. So from hydrogen to nitrogen there is one order, from oxygen onwards there is another order. After this we shall see for heteronuclear molecules. So far we have seen for H2 molecule, O2 molecule, which are homonuclear. Now we shall see for heteronuclear. Okay, constructing the MOT for hydrogen to nitrogen molecules. See, below hydrogen, it is same like what we have seen earlier, but there is a small change. That is, the level I have only drawn for 2p. Okay, I have drawn the atomic orbitals for 2p, and we are going to do the linear combination of atomic orbitals for 2p only to get the molecular orbitals. So, what is the change for hydrogen to nitrogen? Is the pi level, the pi orbitals come down, the sigma rises up, and the antibonding remains the same like that of oxygen case. So comparing nitrogen and oxygen, this is the only change you have to monitor. So this change brings about a major difference. So you see why this happens. Why the sigma level rises atop till nitrogen. The reason is in hydrogen and nitrogen molecules, the molecules are a little smaller. So the 2s and 2p levels, they are going to be of similar energy, 2s and 2p. So there is going to be a little bit of interaction between 2s and 2p. So this is called 2s 2p mixing. So 2s 2p mixing is there in hydrogen to nitrogen. That results in the 2p, the sigma 2pz level rising up. That kind of a mixing doesn't happen in oxygen. So repulsion is not happening. So in oxygen you have sigma level down and pi level up. I will describe you in detail in some other videos, okay, why this happens. So now I am going to fill it. Suppose if we take it for nitrogen. Now we have learnt the basics well, so we don't have to do the molecular orbital construction for 1s2, 2s2 and all. You would directly go for 2p because there is the game changer, right? 2p. So for nitrogen, what is the p configuration? It is 2p3. So I start doing the 2p3 alone. 1, 2, 3, 1, 2, 3. Totally 6 electrons. So how do I fill? 1, 2, 3, 4, 5, 6. 6 electrons are filled now. Bonding completely filled, antibonding empty. So this is the very most stable arrangement. Now, how do I calculate the bond order? Half into 6 minus 0. So half into 6 is 3. So bond order of N2 molecule is 3. Now for N2 you see, for nitrogen, if I have N2 minus, then I have to add an electron in the antibonding level, N2 minus. Adding an electron in the antibonding will reduce my bond order. Then if I have N2 plus, I have to remove one electron from the bonding, right? Because N2 will have 6 electrons in the bonding level. N2 plus will have 1 electron removed. This will also reduce the stability. So here also bonding order is going to decrease. So for N2, with respect to N2 nitrogen molecular ions, if it's going to be plus or minus, I will have a reduction in bond order. The only species having the greatest bond order will be N2 without any charge. N2 has a bond order of 3. For other species, the bond order will reduce. Okay? So you can do it. Just do it for the 2p alone. Now for a heteronuclear molecule. Now I'll do it very quickly to how to find the bond order for heteronuclear molecule at Cn minus. See, Cn minus, you might feel it's different, because it's not a homonuclear molecule. The energy levels might vary. See, when our molecule is homodiatomic, the atomic orbital levels are going to remain the same. But in case of a heteronuclear molecule, the diagram wouldn't be like this. It would be something different. But I'm going to teach you a trick by which, without taking use of the diagram, you will be able to do it. Okay. So for Cn minus, how do I do it? See, carbon. Count the electrons. Carbon, how many valence electrons are there? Or how many p electrons are there for carbon? P2. For nitrogen, how many p electrons? P3. And you see there is a negative charge, minus. So I have to add one more electron. So sum up the electrons. So one more electron I have to add because of a negative charge. Now sum up the electrons. 2 plus 3 plus 1. It is 6 electrons. So this sum is enough for me. Just this you have to find. So put the 6 electrons into the orbitals. See. First start from the lower. Since Cn, Cn comes under hydrogen and nitrogen category. So my pi comes below, then comes my sigma. So how do I fill the electrons? 6 electrons. 1, 2, 3, 4, 5, 6. It is done. So what is the case? How do I predict the bond order for Cn minus? It is a diatomic molecule and the bond order is also 3. Cn minus is same like nitrogen, correct? So I can say Cn minus and the nitrogen are isoelectronic. Which one? Cn minus and nitrogen are isoelectronic and isostructural molecules. So you can do this. So similarly you can try for any other. Now we are going to learn how to find the bond order for polyatomic molecules. Polyatomic means basically having atoms more than 2. So here I have a molecule NO2, nitrogen dioxide, with 3 atoms. So I am going to find the bond order but without using my diagram. Okay. Remember, this formula is only for polyatomic molecules. This particular formula not for diatomic molecules. The formula goes like this. The bond order is given by total number of bonds to central atom divided by total atoms to central atom. That means you have to count how many bonds the central atom has. 1, 2, 3 bonds. And how many atoms are there? 2 atoms. So divide that by the other one. So what do I get? It is 3 by 2. So I can say the bond order of this molecule is 1.5, or I can say the bond order of nitrogen in this molecule is 1.5. So this is a simple question. Sometimes questions can be asked like, how do you relate on the stability of a few polyatomic molecules? So for that you have to use this particular bond order formula. Very simple. Number of bonds to the central atom. How many bonds are there? Divided by number of atoms, linking atoms to the central atom. Divided, you get the bond order directly.
Ask the atoms.